primarily on different loss functions, so the loss functions that motivate support vector machines and logistic regression, and then we'll touch on a few other topics such as nonlinear function classes, such as neural nets, and evaluation metrics. Okay, so homework 1 is due tomorrow, be graded in about a week. Homework 2 will be released tonight or sometime tomorrow, and will be due a week after. There's a recitation on Thursday on linear algebra and some concepts related to vector calculus and matrix calculus. So if you're unfamiliar with that, please consider attending the recitation on Thursday. So let's just start with a recap. Hopefully this is going to pretty much review at this point, but let's just start here. This is the basic recipe for supervised machine learning. We start with a training data set that's supervised, which means we have XY pairs where Y is the prediction target. In the simplest case, Y might be a binary classification task. We choose a model class. In the simplest case, again, a linear model class, which means that the scoring function is a linear function of the input features, X. We choose a loss function that characterizes the mismatch between the correct prediction target and our prediction. In this case, we're going to choose squared error. And then this all gets baked into a learning objective that minimizes the sum over losses over your training set. And the goal is to find a function or model within our model class that has minimal loss on the training set. So this is the basic recipe. We talked about also the bias variance trade-off, where if we are choosing between different types of model classes or function classes for our learning task, then there are different sources of error on the true test distribution that we need to think about when we're doing training. Bias happens when your function class is too simple, and even if you have infinite training data, you can't actually fit this data very well. Variance happens when your function class is too complicated, at least relative to the amount of training data you have. And so if we were to draw an arbitrary sample of that size from the test set and train on that, we would get wildly differing predictions. And that happens when your function class is high variance. And so for any finite training set, we need to understand how to balance the bias variance trade-off in order to train a model that has the best performance on the unseen test data. So here's sort of the complete pipeline where we left it at the end of last week. We start with the training data. We choose a function class or a family of function classes, linear, quadratic, cubic, etc. We choose a loss function, actually possibly a family of loss functions. That's something I didn't really talk about, but it's also something else that you can choose a family over. And we just do some sort of validation where we take our training data and we split off a piece of it into what's called a validation set. Sometimes you do this in a round robin fashion. That's called cross validation. And from that we can understand have a sense of the bias variance trade-off, or at least the overfitting potential of these different function classes on this training set. And the last thing that we covered at the end of last week, which actually we spent almost an entire lecture on, is how to actually solve this optimization problem. What is the actual learning algorithm? And the dominant learning algorithm these days is stochastic gradient descent and its advanced variance thereof. And so this is sort of the complete pipeline where we left it. Any questions on that? Okay, so today we're going to go beyond least squares linear models, which is what we by and large have focused on in the first 2 lectures. So in particular, we'll talk about support vector machines and logistic regression, which are also linear models, but optimized for a loss function that's a bit more sophisticated than squared loss. We'll touch a little bit on artificial neural networks, which are nonlinear function classes. And we'll look at different ways of, and as we look at these concepts, we'll look at different ways of interpreting how these methods are derived. And finally, I'll end the lecture with a short discussion on different ways you can actually evaluate how one model is doing beyond just accuracy, which is relevant for different applications. OK, so let's start with the first. So this is, again, review. We're here looking at the geometry of 2 different loss functions. One is squared loss. The other one is 0-1 loss. If the target that we want to hit for this example is y equals 1, then squared loss has a quadratic shape, because it's a squared loss function, around f of x equals 1. So as f of x, the prediction, deviates from 1, we pay a penalty that is the quadratically growing as we deviate from 1. In 0-1 loss, we typically take the sign of the raw score function, so the sign of f of x for binary classification, And then we look at if the sign agrees with the sign of the target. So if the sign of the target is +1, we want f of x to be positive. Otherwise, and we pay a loss of 0 if that's the case. Otherwise, we'll pay a loss of 1. So that we get the answer right, yes or no, in terms of binary classification. And one of the challenges that we had to deal with is that even though 0-1 loss is sort of the loss function you ultimately care about when evaluating your machine learning model, it's hard to actually directly optimize for this machine learning model because it's hard to actually differentiate, right? The derivative of 0-1 loss is either 0, in which case you have no information how to improve your model, or it's discontinuous, it's undefined, right? At the point of discontinuity. Whereas in square loss, you could just take the slope of the loss function to understand where you need to push the scoring function to reduce the loss. So just to recap, 0-1 loss is considered intractable in machine learning because it is flat or discontinuous everywhere. And therefore, it is very difficult to optimize using methods such as gradient descent. And the goal then is to optimize some sort of surrogate of 0-1 loss that we feel behaves similarly to 0-1 loss, but is much easier to optimize. And today, we'll start with the Hinge loss. And to get to the Hinge loss, we'll look at support vector machines. How many of you here have seen support vector machines before? So it is about 2/3 of the class. OK, so this should be a review for most of you. But perhaps this class will offer a different perspective than the ones you've seen before. So support vector machines are also known as max margin classifiers. And so we'll start with an intuition. So suppose we have 3 possible linear functions that we're considering. In reality, of course, there's a continuous number of such linear functions, but let's just consider 3. And so we have positive examples and negative examples. So just on the surface of it, H1 is probably not the best one because it doesn't get 0 error. However, H2 and H3 both get perfect classification accuracy on this training set. And so can someone tell me why one might prefer one over the other? Why one might prefer H2 over H3 or vice versa? Yes?
Well, H2 gives you like the perfect classification on your training data. H3 looks better because for the actual true distribution, it'll probably divide the 2 classes better, given that maximize the margin.
OK. So one of the reasons why H3, so to rephrase your answer, one of the reasons why H3 might be preferred to H2, I mean, it's sort of intuitive because H2 looks like it's close to getting some examples wrong, right? One of the ways you can actually think about it a little bit more rigorously is that you can think about the distance of the closest point to the hyperplane. So what is the closest that H3 is to getting an answer, one of the answers wrong? And what is the closest that H2 is to getting one of the answers wrong? Recall that this training set is a finite sample from a true distribution of test cases. And so there may be a test case, for example, there may be a test case that's similar to this guy, but maybe just over here in the true distribution. If that were the case, then H2 would get that example wrong. But H3 would still get that example right. And so the way you formalize this concept is it's what's called a margin. And so let's recall the definition of a hyperplane distance. This is something you learned in your standard geometry class early in college or late in high school. Or I guess for you kids, maybe early in high school, who knows. So a line is a 1D hyperplane. A plane is a 2D hyperplane, and generically a hyperplane refers to a linear equation, a linearly defined surface that is in many dimensions, more than 1 or 2, which includes line and planes as special cases. And it is defined by a normal vector or a tangent vector and a bias offset term, W and B. So exactly the same definitions, the terms that define a linear function. The distance of a point to a plane is this formula. It's a very well-known formula. You basically take the absolute score, and then you divide by the norm of the tangent vector. We often use the sign distance here in machine learning because we care if it's on the positive side or the negative side of the hyperplane. and so we often don't take the absolute value. And a linear model, the score of a linear model, which basically is this guy without dividing by the norm of W, you could think of that as the unnormalized signed distance from a point to the hyperplane. And so, if you think about it geometrically, we have this line that separates positive and negative examples. The tangent normal to this line, or the tangent vector, may not be normalized. The tangent vector to this line is our weight vector. And how far this line comes from touching the origin is determined by the bias term. So this is sort of a more geometric interpretation of what linear models are doing. So from this geometric interpretation, we can think about the margin. So the margin of a data set under the linear model, the margin of a data set with linear models is the hyperplane that has maximal margin within all linear models. So the margin of a specific model is simply the closest point, is the distance of the closest point to the line, or the hyperplane. And the margin of this function class of linear models is the model that maximizes the margin, so the maximal margin model. Okay, so that's the intuition. Now we want to find the linear model that has maximal margin on this training set. That's sort of the geometric motivation. Okay, so we're going to assume that the data set for now is linearly separable. We'll look at the case where it's not linearly separable in a little bit. But for now, let's just assume that the data set is linearly separable. And okay, so we want to find this H3 in a continuous optimization problem rather than just looking at three discrete cases. So we're going to solve an optimization problem. And so if we just literally take the definition of a margin, of the max margin from this previous slide, then it's literally this optimization problem, right? We want to find the WB that maximizes the minimum distance to the of a point to the line, subject to perfect classification accuracy. So this looks a little bit like the machine learning problems that we've seen before. At least there's some maximization or minimization going on. But it's also quite challenging, right? So, and to see that, we can look at the fact that a variable that we're optimizing. So one of the free variables that we're optimizing, W, appears in both the numerator and the denominator of this objective function. What does that mean? That means, let's assume for simplicity that B is 0, just for simplicity. If we scale up everything, if we scale up W by a factor of 10, the answer stays exactly the same. So in other words, there's an infinite number of possible solutions to this optimization problem as stated. Of course, when I say you can scale everything up by a factor of 10, everything stays the same, that sort of implies that, okay, even though there's an infinite number of possible solutions, perhaps they're all qualitatively similar, or they mean the same thing. So is there a way to sort of collapse this space of essentially identical solutions into a single solution? And the way you do that in optimization is you hold either the numerator or the denominator fixed, and you optimize the other one, right? So for example, we can hold the denominator fixed, in which case we say, okay, we only care about W's where the norm of W equals 1. Because if we scale up W, it's the same solution, essentially. Everything's just scaled up. So we're just going to hold W to fixed in terms of its norm and optimize for the numerator. This will actually give you the same answer if you can solve this optimization problem. We could also enforce the numerator. So let's say instead of holding the denominator fixed, we hold the numerator fixed instead. What does that mean? That means that the minimal, we want to find the W, we'll want to find a W such that the minimum distance of a point to this hyperplane is 1. It's exactly 1. In terms of, the minimum unnormalized distance is exactly 1. If that's the case, then this optimization problem, if we use this intuition, then this optimization problem, the numerator just equals 1, and we're simply finding the W that maximizes 1 over its norm, which is equal to minimizing the W that minimizes its norm. That's down here. So if we hold the numerator fixed, then the numerator just becomes 1. Then it's argmax of 1 over W, the norm of W, which is equal to argmin of W. And because the quadratic function is monotonic, it preserves the same optimal solution. This is equal to argmin of the norm of W squared. And this turns out to be the formulation we want to use because it's more convenient in terms of optimization. And I'll touch up on that in more detail in the next slide. Are there any questions right now in terms of the high-level sort of roadmap? Yes?
So the first formulation, it's like good to me because you're not losing any generality, but by scaling down, like you're still maximizing these small hyperplanes. But like, I don't see that. I don't see why that's true the second formulation. Like, is there a nice geometric?
You mean this one?
Yeah.
Right here?
Like, yeah, for fixing the denominator, that's all fine because it's like the hyperplane is described as like the vector of any. So you're not losing any generality there, but I don't see why that's
OK, I think it might make more sense if I go on to the next slide. I think this will answer your question. Are there any other questions at a high level? Yes?
Just a quick question about the margin. So
Yes.
when you're calculating the margin, you're finding the minimum on just one side or both?
So it turns out that it's going to be symmetric, right? So for example, if I slide this guy up, this is the minimum margin. If I slide this guy down, this is the minimum margin. It's going to turn out in practice that the minimum these two quantities are equal at the optimal solution. Because you want to maximize the margin, right? So if I slide this up, then this is the margin and it's smaller than this. If I slide it down, this is the margin and it's smaller than this.
So you're effectively like looking only in the space of hyperplanes where the margin is equivalent on both
The
sides.
positive and negative margins are equivalent. I mean, it's not explicitly optimized for in the optimization problem, but that's a consequence. Yes?
So the last one, you can the argument of the norm of W with parameters W and B. So what does B mean in this case? It's not even in the target you're optimizing.
So you want to enforce that this is true. So there exists sets of W and B where this is not true. So so this will become obvious in the next slide. I only care about W and because this is not as formal as the next slide is going to be. I only care about the W and B such that this constraint is true. So that precludes some possible W and Bs. And of those W and Bs, I want to find the one that has the smallest 2 norm on the W. OK, so I think it's going to be helpful if we move on to the next slide. So this is the formulation of a support vector machine, also known as a max margin classifier. And here is the idea. We are going to find the W and B that minimizes the square root 2 norm of W. And I'm going to divide it by half. This is common in the convention simply because once you get into the nitty-gritty of the formula, divided by a half makes certain interpretations easier to do. Such that for all training data points, the unnormalized sign distance multiplied by the actual sign of the target is at least 1. No less than 1. So this is the optimization problem for the support vector machine learning objective. OK, so here's the margin. Right here. So I'm enforcing that for the positive examples, W transpose X minus B is at least 1. For the negative examples, W transpose X minus B is no greater than minus 1. And the margin is this. You can prove it's using standard geometric reasoning, that the distance between this guy and this guy, the distance between these two, at least when measuring in terms of the perpendicular direction to this hyperplane. So they may be offset by a little bit, but ignoring that, just the distance to the hyperplane, the sum of the two is equal to 2 over the norm of W. Which means that the margin, the actual margin, is W minus B divided by the norm of W. So it gives you the equivalent class of solutions. Because if you enforce the numerator to be 1 and you solve this optimization problem, and you can prove that the distance from this line to this point, if you actually do the actual normalized distance, is this exact definition of point to a point. So it turns out that you can constrain the numerator or the denominator. They will both collapse the set of infinite solutions to a single one, infinite identical solutions to a single one, and they can both give you the full expressive class. Okay, so there's a few things that are interesting about this learning objective and the subsequent solutions. So here's one. Suppose I remove this data point. What changes in the solution? Nothing. If I remove that data point, again, nothing changes in the solution. In fact, the solution only changes if I remove a data point on the margin or if I introduce a new data point that's within the margin. So what does that mean? That means that this solution is quite stable, right? The set of possible data points that I have not, so if we think about the true test distribution of data points and the fact that we only have a finite sample from it, there's only a very small set of unseen test examples that may exist that could change our answer. Most data points that we could collect in the future from the test distribution will not change the answer of this classifier. And therefore, it's stable. Again, this is for the linearly separable case. But any questions on that before I move on? Okay, so now let's talk about the non-separable case. And so I just added 2 data points here. And if I did my geometry right, which I may or may not have, let me see here. I think this data set is not linearly separable, just barely. And so for this particular solution, we could now resolve the whole thing, try to find a different solution. But for this particular solution, we have 2 data points that violate the margin requirement. This is called the soft margin support vector machine. The previous example is the hard margin support vector machine. And so here's the formulation of the soft margin support vector machine. And this is the formulation that will lead us to a new loss function that is a good surrogate loss function of the 0-1 loss. So I've augmented the loss function with a new term, so the learning objective, with a new term. So these are called what are known as slack variables. Let's see here, maybe. Yeah, so these are what's known as slack variables. They're non-negative, so they're at least 0. And we want to minimize them. So they're only going to be greater than 0 if they interact with this constraint right here. And what does this constraint say? It says that if a data point is inside the margin, then I pay a penalty that's linear in the amount of margin violation. So in particular, the sum of the slack variables is equivalent to the magnitude of this margin violation plus the magnitude of this margin violation. So what that basically means is, okay, maybe there are a few data points that lie inside the margin because the data set is noisy or the data set is not completely linearly separable, but the data set is perhaps mostly linearly separable. So then I'll just pay some penalty in terms of these slack variables and otherwise try to find a max margin classifier. Right. So the size of the margin versus the size of the margin violations is one of the fundamental trade-offs that we're making here with SVMs. So capital C here is a constant that you set in the beginning of learning that says if C is very large, I really care about minimizing the amount of margin violations. If C is really small, I can tolerate a lot of margin violations as long as I can find a really stable hyperplane. So this is the formulation of SVMs that most people use in practice because, of course, most of the time in a real data set, you won't get like a linearly separability with a really big margin. OK. Let's move on to the loss function. So now I'm going to introduce the hinge loss, which is a new loss function. It's different from 0, 1 loss, and it's different from squared loss. And here is the definition of the hinge loss. So again, the target that we want to predict is +1 right here. And the green line is the hinge loss as we vary the raw score of the linear function. And so if the linear function's score is at least 1, then we pay a loss of 0. And as the linear function score becomes less than 1, we pay a loss that increases linearly with how far the function score is from 1. And so we could write that out mathematically using this formula, which is the max of 0 and 1 minus y times f of x. This is exactly the formula for the slack variable. So if you actually reason about the consequences of this optimization problem, of what the slack variable must be, right? It must be at least greater than 0, and it must be at least as great. It must be big enough so that this inequality is satisfied. Otherwise, it should be as small as possible. So the consequence of those 3 facts, imply that this is the formula for the slack variable. And so the slack variable is exactly the hinge loss. And so what we're actually optimizing here is a trade-off between some measure of the stability of the function class, also known as regularization, which we'll talk about in the next lecture, and hinge loss. So there's a few things that are interesting about the hinge loss. So yeah, that's regularization. We'll talk about that more in the next lecture. So there's a few things interesting about the hinge loss. First, if you're making a misprediction, so which is where on this side of the prediction, then you get a slope, right? You get a slope in the loss function that's not 0, which means you have if you take the derivative, you have a signal of how the scoring function can improve in order to get lower loss. And it's but on the other side, if you're making a really good prediction, well, that's great. It's great that you're making a really good prediction. You're really confident this label is positive. But we're going to make it flat over there so that we don't, if you think about it compared to squared loss, right? So if we care about classification, we don't really care if the score is 1 or 3 as long as it's positive. And so if we care about optimizing for binary classification, minimizing square loss is a little bit weird because we pay a penalty for being more confident that the label is positive. Whereas hinge loss says it's okay. We won't penalize that. We'll just keep the gradient. We'll just keep the slope flat in that case. And we'll only have a non-zero slope when the model starts making predictions that are either wrong or close to being wrong. Right? If the prediction is inside the margin, then I start paying a little bit of loss. And if the prediction is just wrong, I pay more and more in loss. So the hinge loss is one of the more popular loss functions that people use when trying to optimize for classification accuracy. Any questions on that? Okay, so I wanted to just touch on the perceptron algorithm again now that we've seen the hinge loss. So this is the perceptron algorithm that we've seen before. And we looked at this algorithm, and then at the end of the last lecture, we hypothesized or deduced a loss function that this algorithm is implicitly optimizing, and that's the perceptron loss right here. And the perceptron loss and the hinge loss look very, very similar to each other. The main difference is that in the perceptron loss, we only start paying loss, a non-zero loss, if we actually misclassify. Otherwise, in the hinge loss, we start paying a non-zero loss as soon as our prediction is within the margin of possibly being wrong. Okay, so just to summarize for support vector machines, we've actually looked at two interpretations of support vector machines. One is a geometric interpretation. We want to maximize the margin. The second one is a loss minimization interpretation, which is the kind of interpretations that we've been studying very extensively thus far in the class, and will continue to do so into the future. That's sort of the bread and butter default interpretation in machine learning. And so in the loss minimization perspective, we define a new loss function called the hinge loss that is a surrogate to 0-1 loss that we can optimize effectively in a standard machine learning optimization setting. It turns out that these two interpretations are mathematically equivalent to each other. You can derive the support vector machine approach from either interpretation. You can establish equivalence between the two and so this actually speaks to the idea that perhaps the margin concept is somehow fundamental because one can reason about it from multiple perspectives that are all correct. So, sorry, any questions on this? I should just mention that this is something that will come up often in machine learning and related computational mathematical topics, where if a concept is very fundamental, it gets re-derived from different perspectives over and over and over again. And each person may have their own favorite perspective, and indeed, across all of machine learning, the loss minimization perspective is perhaps the most uniformly popular. But all the perspectives are actually correct. Okay, so just a comment about optimization. The hinge loss is not smooth. It has a point that is not smooth at the f of x equals y. That point is called the hinge. In fact, that's why this is called the hinge loss. It's the point where the slope goes suddenly in a discontinuous way. The slope goes from 0 to 1 or minus 1, depending on how you look at it. So how do we optimize for this function if it's not differentiable? The good news is that stochastic gradient descent basically still works. In practice, people do something called subgradient descent, and we'll talk about that in the next lecture. If you know what subgradients are, great. If you don't, we'll touch on it next lecture. But by and large, nothing much needs to change in terms of your SGD solver. Any questions before I move on to logistic regression? Yes?
Is there any reason not to use squared hinge loss so that it would keep this continuity?
Right. So the reason, if you use squared hinge loss, you would pay a penalty that increases quadratically with the amount of margin violation. Right. So there's two issues here. One is, do you want to do that? Sometimes the answer is yes, sometimes the answer is no. You don't want to do that. Sometimes your data set has some crazy outlier that was maybe mislabeled or something. And if you're paying a loss that scales quadratically, it can overly influence the outcome of the learning objective. Second, it turns out that with hinge loss, you can actually say something pretty fundamental about this optimization problem. So there are many there are many learning algorithms beyond SGD that can solve this problem very quickly. And the reason is that for the hinge loss, I know exactly where the loss goes to 0 because it's a linear function, right? The locally linear extrapolation. So in quadratic loss, we make a locally linear extrapolation of around a point that we're optimizing for, and then we take a small gradient step. For hinge loss, that locally linear extrapolation is good for a long, long time. And that has consequences in terms of speed of optimization, although that's beyond the scope of this class.
So this is an alternative.
So this is a quadratic program. So a quadratic program is a minimization problem that has a quadratic objective function and linear constraints. Or I believe that's the actual definition. The constraints may be more complicated, but let's just stick with linear constraints. So this is actually a quadratic objective function, right? It's all the terms. So you could write out this minimization problem, the objective function, as a quadratic, as a second degree polynomial, right? W squared linear plus a linear function, the slack variables. So the free variables are W, B, and the slack variables, and it's a second order polynomial in all the free variables. And the constraints are also linear. So the free variables, again, are W, B, and the slack variables. All the constraints are linear inequalities, first order polynomial inequalities. So this is a quadratic program. So the question is, how do we solve this quadratic program? Yes?
So even if the data is like linear separable, you will still gonna have to decide there because like you require this like y times something like is larger than y.
Yeah.
Like even if it's linear separable, it's still.
If you know for a fact that the function is linearly separable, you don't need the slack variables. But suppose this data point didn't exist, and this data point did exist. I could still, if I talk to my domain expert who's using machine learning, and I'm the machine learning engineer, my domain expert can still say, well, actually, I think this data point is an outlier. Even though this function is still linearly separable, without ignoring this data point, if we only have this data point, this function is still linearly separable, but the resulting classifier is not one that I would like. I think this might still be an outlier. So even if your data set is linearly separable, there are cases where you still want the slack variable because you might have some outliers, even in the linearly separable case. Okay, let's move on to logistic regression. So here's the function class for logistic regression. It's also a linear function class in terms of the actual scoring function, but it uses the scoring function in a kind of a different way compared to what we've seen so far. In particular, logistic regression models the probability that your target is 1 versus, I guess in this case, -1. So if y is either 1 or -1, we're going to model not just the prediction, do we think 1 is 1 or plus or minus, but what is the probability? And the way we do that is we take the linear score, this guy, and we push it through what's called the sigmoid function. This is the sigmoid function down here. And we get a formula that looks like this. So what does that mean? That means that if we look at the score, the raw score, and multiply by the label, in this case, and as that score increases, we think the probability that the label is consistent with y goes to 100% very quickly. And as that score decreases, we think the opposite label is true, with a probability that goes to 100% very quickly. So this is logistic regression. This is just a different formulation of the same thing. You could just do some standard fraction simplification to get from one to the other. These are called log linear models often. And so that's logistic regression. So it's a linear function class, but instead of but for the raw score, instead of taking the sign, we push it through a sigmoid, and we locate, and that converts it to a number between 0 and 1, and we use that to compute probabilities. That's basically what's going on. Okay, so let's try to train this logistic regression model. So again, we have the same training set, x, y pairs, y is binary, so in this case +1 or -1. And this is our learning objective. We're going to find the W and B that maximizes the product of the probabilities that our model predicts the true target given the input x. Can anyone tell me why we are maximizing the product of the probabilities? Yes?
If you assume that all of your data points are drawn independently, then multiply the probabilities together cross-term.
Correct. So the law, and we'll touch on this in recitation, in the probability recitation later on in this class. And so right now we're not going to delve too deep into probability, but just to rephrase your answer, if we assume that all the data points are sampled independently from the test distribution, then what we actually want to do is maximize the probability that we get everything correct. So our original goal, let's say conceptually, is to maximize the probability that we get everything correct. Or maximize the probability that we get as much of it correct as possible. Because everything's sampled independently, according to the laws of probability, that means that that factorizes the probabilities multiplicatively into the product of the probabilities that we get each individual one correct. And if you're familiar with probability, this is something you should already know. If you're not, we'll have a probability recitation later on in this class before we get into probabilistic models in more detail. So why might one use logistic regression? So SVMs in many applications, or at least the Hinge loss, can often be better at classification, assuming that a margin exists or a margin exists subject to throwing away a few outliers. But suppose we want to predict calibrated probabilities, right? Suppose we want to be able to predict the probability that something is a positive label rather than a negative label. Well, okay. So oftentimes you get curves that look like this. So here's a model that was trained. In this case, it was a decision tree, which we'll cover next week. But the same thing happens with SVMs, where as the raw score increases, the probability increases in a nonlinear way. And in fact, this probability increases in a way that suggests that we should model this using a sigmoid function, this S-shaped curve. And so if you want calibrated probabilities, and not just a hard prediction, positive or negative, then logistic regression can offer can be useful in sort of training a model that has calibrated probabilities. Okay, so this is the learning objective. This is the definition of the function class. Now I want to talk about log loss. So here's how log loss works. This is a maximization problem over a product of terms. I'm going to convert it to a minimization problem over a sum of terms by taking the negative log of the objective. if I take the negative log of the objective, of course, I convert it. If I take the negation of something, that converts a maximization problem to a minimization problem. And then if I take the log, well, the log of a probability is equal to the sum of the log of the product of terms is equal to the sum of the log of the terms, just by the law of logarithms. And so we get this guy right here. And now this looks like our standard machine learning objective. Minimize something that's the summed over our training examples. And this term is called log loss. In particular, if f of x is our raw scoring function before we push it through a sigmoid, then the log loss looks like this. And so now I'm plotting it. So that's the purple line. So I'm plotting here. So the target, again, is +1. So the target prediction is +1. And so this is the behavior of different loss functions as I vary the raw linear score, f of x. Note that at this point, f of x doesn't need to be linear. At this point, f of x could be anything. It could be a neural net. It could be a cubic polynomial. Everything that I'm describing here is at the level of what is the raw score of our model. Of course, right now everything is linear, but all of these things extend. All these concepts of loss functions extend to when we work with neural nets. Just as an aside. But okay, so as our raw score increases from -2 to, in this case, +3, 0,1 loss. Again, we see a discontinuity at f of x equals 0 as we go from a negative prediction to a positive prediction. Hinge loss has this linear behavior until we hit f of x equals 1, in which case we have this flat behavior, I guess, which is also linear, but it has no slope. And log loss is something that looks kind of like hinge loss. And in fact, if you if you take the limit as f of x goes to -infinity, it becomes a linear function. And as you take this limit as f of x goes to +infinity, it becomes 0. So it looks a lot like hinge loss, just a smoothed version of it. Yes?
Could you add some parameter into the exponential such that the log loss curve more closely approaches the hinge loss curve?
Yes, you can. So if you raise these guys, these individual terms, to a power. So if each of these terms is raised to a power alpha, as alpha goes to infinity, you get hinge loss. I believe that you're putting me on the spot, but I believe that's correct. Yeah, I believe that's correct. So you raise each of these to a power alpha, and as alpha goes to infinity, you get hinge loss. Yeah. And as alpha becomes way greater than 1, it looks more and more like hinge loss.
Is there a reason for writing it like that in the log loss instead of if you divide?
Is there a reason why I wrote it this way? So in terms of optimization, this is not the most convenient formulation. That's certainly true. In terms of reasoning about the comparison between hinge laws and log laws, I think this formulation makes more sense. But yeah, you're certainly correct that that this formulation is more convenient to work with in terms of when you're optimizing. Okay, so this is something you guys can probably all work out yourself, but just give you an example for the gradient. Let's see, nothing special here. We just use the definition of the negative log, and so of the probabilities, and we get something that looks like this. So this is the this is the numerator, this is the denominator, because the numerator is just this guy. The log cancels out the exponent, so we just get, the log cancels out the exponentiation, so we just get the exponent back. We take the chain rule, we just apply the derivative, or the gradient operator, on this linear function class, and we just get x here. And then we, we distribute, we distribute the gradient operator to the two terms. And so now we apply the gradient operator to this guy, do some chain rule, some more chain rule, some more chain rule. And eventually we get this. And what does this say? This actually has a kind of interesting interpretation. What it says is, if I'm currently predicting this guy really well, in which case this number is going to be close to 1, then the gradient is going to be really small. If I'm predicting this guy really badly, so this guy's close to 0, then I pay the full linear slope. Right? And in hinge loss, this term is either 0 or 1 immediately as you cross the margin. Yes?
So as you've written this, like, you can directly apply stuff like gradient descent to like log loss and squared loss, but the hinge loss is like, it depends on the parameters, right? Like you can't just go do it, like apply it to 1 minus y effects. That's like only if you, I don't know, normalize stuff such that, the constraint, whatever, the margin.
In fact, people do actually do gradient on exactly that. In fact, people do. So, for example, if f of x is something really big, and therefore 1 minus, if y times f of x is a large positive number, then 1 minus that is going to be a negative number, in which case you're going to just flatten out at 0. If I'm over here, this data point, so this is applied on a per data point level, right? So if I'm over here, this data point applies 0 gradient to the learning objective. If I'm over here, this data point applies the standard gradient magnitude, because it's a slope, it's a linear line, so it's the gradient is the same over here. The only point where you might be concerned is if f of x exactly equals y. So people have different schools of thought. Some people just ignore that case because that case almost never happens in practice, where f of x is exactly y. Other people have do something a little bit careful to check if it's close to 1, and there's some certain more advanced optimization techniques you can use beyond the scope of this class. But broadly speaking, you could apply stochastic gradient descent to hinge loss. It just doesn't work on 0-1 loss, because if you're over here, you get the slope is 0. So the gradient is completely 0. No matter if you're minimizing 0-1 loss, the slope is completely 0, even if you're classifying or misclassifying an example. Okay, so finally, I just want to sort of look at two different interpretations of logistic regression. So in logistic regression, we have a probabilistic model that models the probability of a label given x, which basically is achieved by applying the sigmoid function on the raw score. And when we train logistic regression, we can either maximize the likelihood over a model on the data, or we can minimize log loss, which is a new loss function that we just saw. It turns out, again, that these two interpretations are exactly equivalent of each other. Yeah. Any questions? So now I'm going to spend just a few minutes on feed-forward neural nets. We're going to cover this in detail in week 4. So in about a week and a half, or I guess exactly 2 weeks from today. But I just want to touch on it a little bit. So a one-layer neural net looks like this. This is sort of the way people describe it pictorially. It takes its inputs x and it predicts an output y. And this single neuron looks like this. And then there's a transfer function that, that translates this f of x into the y. Let's say the transfer function is sigmoid. Doesn't have to be, but that's one of the ones that people have studied in the past. Could be another one, sigmoid, hyperbolic tangent, rectilinear, but some transfer function. This is actually logistic regression. A single neuron, a singleton neural network with a sigmoid transfer function is exactly a logistic regression. Okay. Now let's talk about two-layer neural networks. So here we have two layers of neural networks. In the first layer, we have two neurons. Each one is a separate linear scoring function plus a transfer. Let's say it's a sigmoid transfer function. And the outputs of these two neurons are fed into another neuron that does a weighted combination, linear weighting of them, and then pushes that through another transfer function. And the middle layer is also known as a hidden layer, because it is not the final output layer, nor is it the input layer. And really deep neural networks that have many hidden layers. But this is the basic idea behind artificial neural networks. One of the interesting things about this function class is that it is nonlinear. Because of the nonlinear transformation in this black box in the hidden layer, the final output of this function is a nonlinear function of the inputs. And in fact, if we have enough hidden layers, so if we have enough neurons in this hidden layer, we can approximate arbitrary functions. Okay, so a deep neural net is simply an artificial neural network with many hidden layers. That's all. One might want to prefer deep neural nets over two-layer neural nets with many hidden units in the hidden layer. There's a few different arguments. So one is that often for the same accuracy, you get a much more compact model. If you've taken circuits or circuit design, you know that deeper circuits are more expressive than shallow fat circuits. Neural nets, in some sense, have many analogies to circuits. So a circuit with like inputs and 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 OR and add gates and etc. Sometimes they're actually easier to train, believe it or not. And we'll discuss all these things more in the deep learning lectures. The way that people train neural nets, some version of stochastic gradient descent. So, if we can model each individual neuron as a linear function plus a nonlinear transform. So, but internally there's this linear scoring function for each neuron with its own parameters, its own W and B, let's say. Then, if we want to take the gradient with respect to one of these W's, with respect to the loss function, this could be log loss, hinge loss, squared loss, etc. We just do a bunch of chain roll, and we get it. So it's complicated in a uninteresting way, computing these gradients. These days, of course, there are solvers that do these gradients, compute these gradients automatically for you. But this is the basic idea. So neural nets are nothing more than everything we've seen already, just stacks of linear functions with nonlinearities in between, and you train them with gradient descent or stochastic gradient descent, and using just chain rule judiciously, or not judiciously, using chain rule obnoxiously. neuroscience community, when they were studying artificial neural nets from a neural-inspired perspective, they didn't think about it in terms of calculus. They just called it backpropagation. But it's essentially equivalent to gradient descent. But the term backpropagation came from the neuroscience community. Any questions on that? Yes?
Could you just clarify why we have activation functions at each layer?
Yes, okay. So imagine that we didn't have this activation function. Imagine that we didn't have this activation function right here, right? So imagine that this module didn't exist. Then, a linear combination of a linear combination is a linear function. And in which case, we just get back linear logistic regression. Without these nonlinearities, all the layers can collapse down to a single layer. And then we just get back standard linear logistic regression. It's kind of striking, actually, that the only nonlinearity in this whole thing is this transfer function. And everything else is just little modules of linear functions. But yet, if you have an iPhone or a Google Android, and you talk to it and it recognizes what you're saying, it's built on this. Yes?
Is that, like in the previous slide, it just said it approximates any arbitrary function. Is that ability limited by how complicated your neural network is, or how is that like that?
I didn't tell you how many units. I didn't tell you how many units you needed to do this. It's a limiting argument. It's often not practical to approximate quote unquote arbitrary functions, nor is it often desirable in practice. The function that maps audio to language for speech recognition is not arbitrary. So this is just sort of it's kind of an interesting statement, but ultimately, in and of itself, is not extremely useful. Yeah. Was there a question up here? Okay. I want to spend the remaining 10 to 15 minutes or so talking about evaluation measures. This is, for the most part, outside of, for the most part, this is an aside compared to everything else we'll be doing in this class. We won't really focus on this in the homeworks much, but I want to just take a little bit of time to expose you to these concepts because you will find them useful and use machine learning in other applications after you leave this class. So when we evaluate a a model, not training, we're not going to talk about training at all right now, or very little. So we can evaluate classification using 0-1 loss. We can evaluate regression using squared loss. Well, what else can we do? So here's an example, and this is a kind of a toy example, but I think it's it illustrates some ideas. Suppose we're doing cancer prediction, right, of some, I don't know, an X-ray image or something. And there's sort of 4 possibilities in this toy example. In practice, there may be many more. We have the patient actually has cancer and doesn't have cancer. And we have the model predicts cancer and predicts no cancer. Okay? So what happens if the model predicts that the patient has cancer and the patient does have cancer? The loss we incur should be low. If we predict cancer and the patient doesn't have cancer, the loss, let's say it's medium, right? The patient does some extra tests, maybe has a surgery they don't need to, but let's just call that medium loss. If the model predicts no cancer and the patient actually has cancer, that's horrible, right? And the model predicts no cancer, the patient doesn't have cancer, we'll call that low. Okay. This is also known as a loss matrix or a cost matrix. And in particular, this illustrates the idea that we actually the loss function considers positive and negatives differently. We care much more about the positive examples than the negative examples. In particular, if the true target is a positive, we better predict positive. Let's call it a cost matrix. 0-1 loss is the special case where it's symmetric. So in 0-1 loss, we got 0, 1, 1, 0. So 0-1 loss is the special case where you get this, I guess because the way I ordered it, it's an anti-symmetric matrix, but it's a symmetric matrix. Okay, so here's just one idea. People have a few different ways of thinking about this problem, but we could put some numbers on it, right? So if we predict cancer and doesn't have cancer, we pay a loss of 1, and if we predict no cancer and has cancer, we pay a loss of 1,000, just for example. And we can just put this into a learning algorithm right here, like this. There are a few different ways one can go about doing this. This is just sort of one idea. I don't necessarily recommend doing it this way, but I do recommend that you keep this idea in mind because you may find that in your applications something like this comes up, and you know how to search for better approaches than this one. Okay, any questions on this? Okay, so now I'm going to talk about another concept, set of concepts called precision and recall. So in precision and recall, it's built on this idea of true positive, false negatives, and true negatives. In particular, if the true label is positive and our model predicts positive, that's called a true positive. If the true label is negative and our model predicts positive, that's called a false positive. So our model predicted positive, but it wasn't actually a positive. If the true label is positive and the model predicts negative, that's called a false negative. And if the true label is negative and our model predicts negative, it's a true negative. So this is one way. This is a different way of thinking about treating positive and negatives asymmetrically. So precision is basically the true positive divided by the true positive plus false positive. That means if I take everything in this row, which is where our model predicted positive, what's the fraction of items that are actually positive? Right? So for example, if I'm a search engine and I'm giving you 10 results for your search query, and I think those are the positive results for your query, what is the fraction of that that is actually useful to you? Recall says I'm going to take the ratio of true positive divided by true positive plus false negative. That's this guy, true positive, divided by this column, true positive plus false negative. And that says, of all the actual positive events, how many did I actually predict as positive? Of all the people that actually have cancer, what fraction did I actually predict has cancer? Note that these two definitions completely ignore this bottom right cell, the true negatives. Let's see here. Yeah, so we care more about positives. Oh yeah, sorry, I forgot. The F1 score is simply the harmonic mean between precision and recall. So we can often plot these precision recall curves. So recall that we had this bias term, this B. One thing that people often do in practice is they throw away their original B, and they just vary that B. They just move that B up and down between negative infinity and positive infinity. And once you do that, you get this curve of different things you predict as positive or negative. And so this is called a precision recall curve. And the best model, if you get 100% accuracy, you get over here. You have perfect precision and perfect recall. If you care more about recall, then you want high recall. So high recall over here, perhaps at the expense of precision. But if you only have a very limited attention span, like I only have time to look at 10 things, I only have time to look at 10 PhD applications, and I want to make sure the person that I admit is a good one, then I care about precision, right? Sorry, it's PhD application time. It's on my mind. And so it really depends on the use case. If I don't want to miss any actual positive result, I care about recall. If I only have time to look at 10 things, I care about precision. And when we look at these models and we vary the threshold by which we classify as positive or negative, we get what's called a precision recall curve. I, of course, can't classify everything as positive. It's not a useful classification, but I could, in which case I get 100% recall and essentially zero precision if the positive examples are the rare events. And I could get 100% precision. If my model, if the thing that my model is most confident is actually positive, then I could vary my threshold so that I only predict one positive. In which case my precision is 100%, but my recall is awful. And so a model has a better performance of the precision recall curve if it's on top of the other model, right? So A dominates B on the precision recall trade-off in this example. Okay, so I want to talk about ranking measures next. I think this is the last thing we talk about. So let's say that we are ranking web pages by their relevance to a search query. And we're going to predict a ranking of, let's say, 4 results, because we know the user will only look at 4 results, only has time to look at 4 results. So we learned some function, f of x, the parameters are w and b, and it scores the results as most relevant to this query, and we sort by that. That's what people do, right? And let's say that result 1 was positive, and result 4 was positive, and results 2 and 3 were actually not useful to me. Then we could talk about precision at 4. So what fraction of the top 4 are actually relevant? And that precision at 4 is 1/2. We could do recall at 4. If we only look at the top 4 results, what fraction of the positives have we captured? In this case, 2/3, because there was one result that ranked 6. So these ranking measures only look at the top of the ranking. Okay, we could do pairwise preferences. So in this case, we have a ranking. So everything on this side, this guy is ranked the best, this guy is ranked the worst. And in this case, if we look at all pairs of positive and negative results, so this guy and this guy, this guy and this guy, we see that there's 2 disagreements. There are 2 cases where a positive result was ranked below a negative result. And that's called the ROC area, or that's related to the ROC area. The area under the ROC curve, and again, you can read about this more if you're interested, is the fraction of pairwise agreements. This is a very common metric for understanding the accuracy of a model when you care about the ranking. And this is sort of the definition. So if we have this example, sorted from left to right, 3 positive results, 2 negative results, the ROC area is 0.5. So basically doing no better than random for this ranking. And indeed, it's basically doing no better than random. Because there are 6 possible pairwise preferences, so between 2 negatives and 3 positive results. And exactly 3 of them are correct. So this guy is correctly ranked above this guy is correctly ranked above this guy, and this guy is correctly ranked above this guy, and there are 3 pairwise disagreements. So the ranking like this is doing no better than a random ranking. And the final thing is called average precision, which is the average under the precision, the area under the precision recall curve. So the total area is 100%, and the area under that, there's a formula for it, is called average precision. And I think in the interest of time, I won't go into the details. Yeah, I'm running a little short on time, so I'll skip that. So finally, other challenges. So these are challenges, in this case, motivated by applications to computer vision, which is one of the more popular use cases for thinking about applying machine learning today that are not yet ready for consumers, but is an active area of industry development. So for example, if I want to do object localization, so in this case, draw me a bounding box around every car in this image. Very relevant for things like self-driving cars. Okay, I can draw many different kinds of bounding boxes. I can draw bounding boxes that are huge. I could draw a huge bounding box that definitely has the car inside of it. Okay, well, maybe that's not so useful, right? And so there's all these notions of precision and recall in spatial domains where I draw these bounding boxes. I want the bounding box to be a tight fit around the actual object. Maybe I want a little bit of maybe I'm okay with drawing a slightly bigger bounding box or not. If I think that, this thing is a car, but the actual correct bounding box is this green one, is that correct or incorrect? Is it some fractional overlap? If I think there's that there's two cars here, but there's only one, what does that mean? So there's all these different ways of evaluating the quality of a machine learning model in these complicated prediction settings that you have to think very carefully about when judging the suitability of your approach for the actual downstream application. Yeah, and it gets harder in videos too, because there's temporal bounding. So if I want to classify someone as running, is it after they've taken their first step? That's the time boundary of this label, because the label is actually over a time interval, or is it before they take their first step when they start running? People disagree. Okay, so just to summarize, I spent the last few minutes looking at different evaluation measures to focus on different scenarios. A lot of them are really focused on the positive examples. Where are the true positive, where are the actual positive examples, and how do we actually focus our predictions and evaluation on that? Because in many real-world scenarios, there's a huge class imbalance. Many things we don't care about, the negative examples, and the few things we care about, the positive examples. Okay, so that's it. Next lecture, we'll look at regularization and lasso. Thanks.